So to continue with binary star systems are kind of like these couples in this photograph. And binary star systems can have planets with them, which are kind of like the grandchildren in the photograph. So we have to know how to classify these a bit better and calculate them better. Let's look into it now. When we are looking at binary star systems, we know that we can have differences in size and in luminosity and in mass for these systems. And we are going to talk about the center of mass. We introduced it briefly with seesawing in the last video. Now we're going to talk about it a bit more. And I hope that you've had some experience with the seesaw. I know that seesaws are being taken out of playgrounds. I know as a mom, I've watched this and I've seen seesaws being ripped out of playgrounds because they're deemed unsafe. But if you understand the physics of the seesaw, it is not unsafe. What the physics of the seesaw means is that you really have to think about the mass of the people involved on the seesaw and making sure that you balance at the fulcrum of the seesaw. So in other words, if you have two people who are about the same weight, then they can be about the same distance from the fulcrum of the seesaw. And you really won't have a problem. One can push off and it'll go off and you have leverage, and the other can push off and you can keep it pretty safe right there. But if you have two people get on the seesaw and really outweigh the other person, well, those people have to cinch up on the seesaw and give a lot less space between the higher mass in the fulcrum and a lot more leverage for the other person who weighs less than their total in order to balance things out. That's where it comes into play when children who are heavier get on with children who are lighter and they don't consider the distance from the fulcrum. Then it can get a little bit aggressive for the seesaw, and I guess kids can get thrown off. But if you understand the physics of a seesaw, not a big problem. So the physics means that there's a mathematical correlation to what I just said. And that means that if we think about right and left of the fulcrum at the equal sign, well, then you have the man in blue who's a mass 1, and he has to have a lot more distance, radius, between himself and the fulcrum in order to balance a higher mass on the right. And they will in turn need to scooch up along the fulcrum in order to make this balance out and have the same amount of leverage on each side. Where does this come into play in binary star systems? Well, it comes into play in the same thing you saw in orbits in your lab with the Earth and the Sun. People don't feel like the Sun revolves around a center of mass, but the Earth revolves around the Sun, and you saw the Sun revolves ever so slowly around a center of mass. You saw it wobble in your orbit lab. That's why I wanted to show it to you. That wobble is caused a bit by the Earth rotating around it, and it's caused even more by Jupiter and Saturn rotating around it. Let's talk about this. When you did your lab, you saw the Sun wobble a bit due to the Earth. And the center of mass for the Sun with the Earth is right outside on the outer layer of the Sun. So there's not a whole lot of wobbling around the outer layer of the Sun for the Sun. However, when you consider the mass of Jupiter and Saturn in a system, that mass and that gravity is something that does pull the center of mass out from the Sun. So that if you increased the mass in that lab for the planet to the mass of Jupiter, you would start to see the Sun really orbit around a barycenter. I could have that lab changed a bit in order for you to note that. That probably would be a good change. So this barycenter, considering more mass, is a bit farther out from the surface of the sun as it is with the Earth. When you think of barycenter, think of barometer, okay? It comes from the Greek word baros for weight, and barometer is measuring the weight of air. So that when you consider the mass of the sun being so big, its radius to the barycenter will be low relative to the mass of Jupiter and Saturn, which has a good sized mass, but they certainly don't have the mass of the sun, and their radius is higher relative to this system. So when we look at the barycenter and their impact on the binary star system, it becomes very important to the law of universal gravitation, which is Newton's tweak on Kepler's third law. Remember, Kepler's third law says that the square of the orbital period equals the cube of the distance between the sun and the planet. Now, Newton said gravity is universal, not between just a sun and a planet. It's between a galaxy and a galaxy, between an Earth and a moon, between the sun and Jupiter. So that Newton really reinforced the idea of the center of mass and the barycenter and put it into his tweak on Kepler's third law. Newton put in the distance from the barycenter cubed, and he put it over the total star mass, or the total mass of the gravitational system with two objects in it. So that in this case, we are looking at binary star systems and star A plus star B. Star A mass plus star B mass. We need to know that distance from the barycenter. And we need to know the orbital period as well. So that, like I said, we need to know both. And when we look at each of these star systems, the orbital period is not that hard to find. When we're looking at a visual binary star system, you can see it right in front of you. And in fact, you can see it on photographs, and you can plot it out and analyze the data. 1948, 55, 60, 65, all the way around to 83. The smaller star is orbiting a center of mass, which is right about here, and the larger star is orbiting that center of mass as well. You can plot out the orbital period. It will be the same orbital period for both stars. This is what is very important. The only way both of these stars can orbit around a center of mass is if they are opposite each other in their orbits. And in order to maintain that opposite dimension, they have to have the same orbital period. So while the smaller star takes a good, 40 years to go around the center of mass, it is moving quite a bit faster in this radius, and this bigger star is moving around the center of mass more slowly, the same roughly 40 years. When it comes to spectroscopic binary star systems, it's harder to tell that orbital period. All you've got is a red shift or a blue shift, and you don't have a lot of information about the orbital period for this. You can take the extent of the red shift, how far it goes into the red, or how far it goes into the blue. You can take the duration of how long that redshift lasts, and you can make some calculations about velocity of the orbital period, but they're going to be estimates. When it comes to the eclipsing binary star system, you can definitely get velocities of this smaller star and the amount of time that it takes to transit the larger star, just as we got a lot of information when Venus transited the sun. So we can get orbital periods for that. There are challenges in knowing the size of the orbit and the distance to the barycenter. It involves the fact that you need to know the linear diameters, the angular diameters, and the distance from the Earth to the binary star system. And on top of those measurements, you have to make sure that those measurements are not distorted by elliptical orbits, which you've learned about, and by angular changes when you are off a trajectory, and you could be like Pluto is 40 degrees off the ecliptic of the solar system that we are in. So those different orbital angles really do distort some of these calculations quite a bit. But when we talk about the area of the orbit and the distance from the barycenter, we are really using the concept of the small angle formula. And what we're doing is we are extending out the triangulation in order to get some of these radii. And I think you can understand that. You're looking at triangulation of a baseline, the linear data, the baselines here for the radii, and the angular diameter that we're seeing for the edges of the orbit, and we're looking at the distance between this binary system and the Earth. So we're using the same mathematical formulas for the small angle formula in order to get these radii in here. It's relatively easy with the visual binary star systems. It's much harder with the spectroscopic binary star systems because we don't even have much information beyond the red shifting and blue shifting and the possible velocities we can get off of that. But we also might have elliptical orbits in here, and we might have angles to those orbits that are just going to complicate things for the spectroscopic binary star systems. With the eclipsing binary star systems, at least we don't have an angle on the orbit. And we know we don't have an angle on the orbit because it goes directly across the orbit of the larger star. So at least we can eliminate that variable that could add in some problems into our calculation. This is a dead-on transit angle right here. We know it's a dead-on transit angle because when we see this, we see a very even difference in the intensity of the brightness throughout the transit. Again, we see an even drop in intensity. Contrast that to this. Here's another really interesting eclipsing binary star system that is found in the Algol star system in the constellation Perseus. It's actually found right in the head of Medusa, which is kind of cool. And this Algol binary system doesn't have that nice even dip. The dip takes an angle to it. So there is actually, we know now, an angle to the eclipsing system where it's off just a bit, and that produces the uneven dip in brightness when the smaller star of the algal system